Put your hand on a car window. Feel the road sliding past. Now imagine moving so fast that in 1 second you could circle Earth more than 7 times. That's roughly what light does. Not kind of fast. That fast. Keep that speed. Don't slow down. Don't stop. Run it for a full year. You still cross only 1 light year. 1. About 9.46 trillion kilometers. Almost 6 trillion miles. I always forget which number hits harder. And then I remember, neither does. Your brain just bounces off both. And the nearest star past our sun? Not 1 light year away. Proxima Centauri sits a little over 4. 4 of those monsters stacked end to end, just to reach the next house on the block. So the first uncomfortable fact is simple. Space isn't merely big. Big is a mountain, an ocean, a planet. Interstellar space is a different category. And a light year sounds like time, right? It isn't. It's a distance built from the fastest speed nature allows. Every time an astronomer says that word, they're quietly telling you 2 things: how far something is, and how brutally long the universe makes you wait to get there. Start smaller, or this never lands. The moon is about 1.3 light seconds from Earth. Point at it, count 1, and light has already crossed the gap. The sun is roughly 8 light minutes away. The sunlight on your face left home before you finished tying your shoes. You're always looking at it slightly in the past. Picture every beam of light as a postcard stamped with the moment it left. The farther it travels, the older the picture gets. Pluto sits in light hours. Then the numbers stop being friendly. 1 year of light travel, 1 light year. Try driving it at 100 kilometers an hour without stopping. You'd need more than 10 million years. 10 million for 1 unit. So use something faster. Voyager 1, launched in 1977, still the most distant machine humans have ever built, crawls away from the sun at about 17 kilometers a second. At that speed, 1 light year takes roughly 17,600 years. Not Proxima, 1 light year. There's the first O. We built a machine, threw it into interstellar space at tens of thousands of miles per hour, and on the scale between stars, it is basically standing still. Our engineering is impressive. Space reviewed the paperwork and stamped it. Adorable. And that isn't because Voyager is badly built, it's because the ruler itself is monstrous. In 1676, a Danish astronomer named Ole Rømer was timing eclipses of Io, one of Jupiter's moons, and the eclipses kept showing up early or late depending on where Earth sat in its orbit. Io wasn't misbehaving. The light was taking different amounts of time to reach us. That observation helped crack something most people still feel in their bones should be true. Light does not arrive instantly. It travels. Today, the speed of light in vacuum is fixed at exactly 299,192,458 meters per second. We define the meter using that number. And nature keeps the speed limit. According to special relativity, nothing with mass just accelerates through it. Push closer, and the energy bill goes insane. Light isn't only very fast, it sits at the boundary of what information and ordinary matter can do through space, which turns the light year into a strange cosmic insult. It's the distance covered in 1 year by the thing that already moves as fast as the universe permits. And even that thing needs a year. Now widen the picture because it gets worse. NASA puts the outer edge of the Oort cloud, that distant shell of icy leftovers around our solar system, out around 1.87 light years from the sun. At light speed, you could travel for a year and still be fussing with the outskirts of home. Then Proxima, at about 425 light years, nearest stellar neighbor, not another galaxy. The next porch light. If the sun were a grain of sand, and you tried to build a neat model of nearby stars, the hard part wouldn't be making the stars small enough. It would be finding enough empty floor. That emptiness is the structure. We call it space, like the word is neutral. It behaves less like leftover room, and more like a moat that somehow stayed the right width. And this is where people reach for the comforting sentence, someday technology will solve it. Maybe, but technology is not a magic word. It's a bill that has not been paid yet. Consider the fastest human-made object ever recorded. NASA's Parker Solar Probe hit about 430,000 miles per hour, diving near the Sun. New York to Tokyo in under a minute, if you want the postcard version. If you could somehow hold that record speed continuously in interstellar space, which Parker cannot, 1 light year would still take about 1,560 years. At the fastest speed our species has ever given a machine. Proxima would still be more than 4 times farther. A lazy documentary would hand you a fake precise line here. If light were 0.001% different, everything vanishes. We're not doing that. Physics doesn't let you twist one constant while pretending the rest of reality sits still. That sounds sharp. It isn't honest. The real precision is stranger. Every observer in vacuum measures the same light speed, even when those observers move relative to one another. Space and time adjust. The limit does not. Your everyday brain says speeds should add. Throw a ball from a moving car and the road sees both. Light refuses that arithmetic. The universe protects the limit by making space and time behave in ways your instincts hate. We didn't discover the ruler was wrong. We discovered our instincts were. That should bother you a little. Because once a speed is woven into how space and time behave, a light year stops being an arbitrary astronomy word. It becomes a physical consequence of the rules underneath reality. A rule that shows up the same everywhere we can test it. So can we beat the distance? Not by building a bigger Voyager. Chemical rockets are great at leaving planets. Interstellar travel asks for a different scale of speed, and the energy required rises brutally as you push massive objects closer to light. Researchers have tried other doors. Breakthrough Starshot, announced in 2016, is a research program exploring tiny, uncrewed craft pushed by powerful ground-based lasers. Stated ambition: technology that could drive ultralight probes to around 20% the speed of light. 20%. At that speed, 1 light year takes about 5 years from Earth's frame. Alpha Centauri becomes decades, not tens of thousands of years. But notice what we had to do: shrink the spacecraft, remove the crew, replace onboard engines with an enormous external laser system, shove materials, aiming, heat and communication into regimes we've never flown for an interstellar mission. Humanity looked at the gap between stars and basically said, what if the ship were almost weightless? And we hit it with a laser. Elegant. Also a useful confession that the problem has not surrendered, and even if a probe reached Alpha Centauri, the conversation still obeys the same ruler. A signal home takes more than 4 years. No live call, no instant command. No turn left, we saw something. Imagine people eventually living around another star. A child is born there. Earth gets the message more than 4 years later. Earth sends congratulations. The child is around 8 before the reply can arrive. Nothing malfunction, no satellite failed. That is simply what 4.25 light years means. Suddenly, distance isn't geography. It's separation in time. The Milky Way is on the order of 100,000 light years across. When you look up at the galaxy, you are not looking at one shared cosmic now. You are looking at layers of history arriving together. Some light started before your grandparents, some before cities, some before our species walked upright. The sky is an archive that pretends to be a ceiling, and 1 light year, the unit that already crushes our fastest machines, is tiny on that scale. That might be the most disturbing part. We can go 1 layer deeper on why the emptiness isn't just scenery. Stars are not gentle nightlights. Some die violently. A supernova can outshine its whole host galaxy for weeks, and it doesn't only throw light. It throws gamma radiation and cosmic rays that can strip a planet's ozone from tens of light years away. Researchers modeling near-Earth supernova effects put a rough danger window around 25 to 50 light years. Inside that range, a stellar explosion is not a pretty show. It's a physics problem with a body count written in radiation. Our sun's closest neighbors sit at 4, 6, 8 light years, close enough to see on a clear night, comfortably outside that kill radius for billions of years running. Pack the neighborhood tighter, the way stars pack in a dense cluster, and you don't get a cozier galaxy. You get a shooting gallery of radiation and gravitational flybys that kick comets inward and shove orbits around. Astronomers studying planet formation in crowded clusters keep finding the same pattern. Close stellar encounters are common enough to tear young systems apart on timescales far shorter than the quiet stretch our solar system has enjoyed. Humans spend years and billions just calculating safe blast radii for a single test site. The spacing out here has held a planetary-scale safety margin at galactic scope without ever sending us the spreadsheet. An accident that keeps passing the inspection is still an interesting accident. So naturally, we want the wall down. NASA and JPL have spent decades on propulsion concepts. Ion engines, nuclear thermal, solar sails, each a real leap over chemical rockets, each still laughably slow against a light year. New Horizons needed about 9 years just to reach Pluto, which is a rounding error next to this unit. Meanwhile, sunlight makes the full 1-year trip for free, every day, no committee, no launch window. NASA has been sketching advanced propulsion since the 1960s. People are optimistic about decades from now. A hydrogen atom does the commute before breakfast. The gap between human engineering and cosmic reality is not motivational. It's humiliating. We throw our brightest minds at a problem, and the universe barely shrugs. So here's what's actually sitting behind that 6 trillion mile number you couldn't hold a minute ago. A distance too large for a human mind to picture. Built from a speed limit we did not negotiate. Preserved by space and time adjusting so every observer gets the same answer. Wide enough, in our quiet stretch of the galaxy, that nearby stellar violence stays a calculation instead of a local event. Expensive enough that our best near-term plan for the next star is a postage stamp probe hit by a laser, still taking decades, still leaving a 4-year silence on the phone line home. Astronomers didn't invent the light year because it sounded dramatic. They invented it because ordinary distances became useless. We can measure the limit, we can build our units around it. We can design machines that crawl closer to it. We did not write the rule. Next time you look at a star, don't picture a bright dot hanging above you. Picture a message crossing a black ocean at the fastest speed reality allows, and still needing years to arrive. That is 1 light year, not empty space, a locked scale, a speed limit, a reminder that the universe runs on rules so consistent even our most ambitious machines have to kneel. And that leaves one question sitting in the silence between the stars. Who set a ruler this exact, if no one set it at all?